Thank you, Lee, for inviting me, and thank you all for coming. I'm delighted to be here out in California. Actually, my main reason for this visit to California is to take care of my grandkids. This is a sort of day away from Seal Beach. So you can tell me afterwards whether it was worth it for you as well as for me. What I want to talk about is something that I've been sort of working on for quite some time, and I think it's a real interesting moment in time in terms of education, particularly science education. And going to try to put in context sort of where we are and what are the really interesting issues and challenges that we face as we think about the assessment of proficiency in science. And a little bit of some of the work that I've been involved in over the last, I guess, 6-7 years related to actually trying to work through what that might mean, not just from an assessment perspective, but also from the perspective of curriculum, instruction, and assessment and how they fit together. So I want to open with this, and it has nothing to do with Lee's heritage. This is a favorite little saying that is attributed to Robert Kennedy about the idea that there's a Chinese curse that may we live in interesting times. It turns out that in the context in which this was given was a very different world. It's also a context that there is no such thing as a Chinese curse. Like, this is a Western invention. But the point about, and what I like about this statement is that it captures the fact that in the education world in general, and in science education in particular, we are in interesting times. And they are times of uncertainty, but they are also times of great opportunity if we capture the moment and think it through and really work it through in some detail. And why do I think that this is the case? Well, I think there's a confluence of things that have happened in science education that span the range from K-12 up through higher education. And they're reflected in things such as the NRC framework for science education and the derivative of that in terms of the next generation science standards. They are captured in the work on the redesign of the AP science courses, biology, chemistry, and physics. And it's also captured in the work that has been done to redefine the science that we want individuals who are entering the medical profession to know in terms of the competencies we want them to have and how that's actually to be reflected in the new medical college admissions test, which has major implications for the teaching and learning of science at undergraduate level. And the reason I sort of connect these dots is I've been involved in some fashion or other with all three of these enterprises, the K-12, the College Board work on AP redesign, and to some extent the MCAT. And I think what's really critical is understanding that if we look across these, we've got a new definition of competence. And I think the NRC framework, which is the one that many of us have seen, really has articulated this in a very clear way, that competence is really the intersection between important disciplinary practices, important disciplinary ideas or core ideas in the discipline, and what they call cross-cutting concepts. And the way that this is reflected is to define competence not as this is what you're supposed to know in the way of core ideas, this is what you're supposed to know in the way of science and engineering practices, this is what you're supposed to know in the way of cross-cutting concepts, but by the intersections of those things with respect to performance expectations, that essentially defines competence as your ability to use your conceptual understanding by demonstrating it through the practices of scientific reasoning and argumentation. And so knowing science means you're able to do something with that science with respect to the practices. And I think, and that's captured in the form of the performance expectations. Also, the view that has emerged, which makes sense, is that competence is really something that develops over time, and that it is not just that you accumulate more knowledge, but that that knowledge becomes increasingly sophisticated and powerful in terms of what you're able to do with it, and it's the product of a coherent system of curriculum and instruction. And if you work in the field of K-12 science education, many of you know that in our science education has been anything but coherent, particularly at grades K through 8. It has been a collection of things in terms of topics, modules, and anything other than a coherent system in terms of where ideas develop over time. And it defines goals for teaching and learning as the sort of the interconnections of these three things: the practices, the core cross-cutting concepts, and core ideas. And so the goal is to have coherent investigation of core ideas across multiple years of schooling. In fact, it defines core ideas as ones that lend themselves to being not only key to the discipline, but ones that can develop in terms of sophistication over time as we come to engage in them through the practices. It defines the goals for teaching and learning as a more seamless blending of the practices with the core ideas. And again, performance expectations that require reasoning with the core disciplinary ideas. And a real shift here from identifying our goals in using vague terms, which we all love. They're great cognitive terms. They're ones that I use all the time, and there's the ones that we've used in standards documents for a long time. They're the two greatest cognitive verbs, know and understand. The problem is we don't know what it means to understand, and we don't understand what it means to know. And we use them as surrogates to allow us to agree about what the standards are, so then people can figure out what their own interpretation is. The difference is now to use terms that capture what it means to know, the kinds of performance: explain, justify, model, predict, describe, illustrate, argue. That this is now the way in which we're indicating what the competence is. And so it's not just that you know something about the particle nature of matter, but you're able to use that knowledge to argue and explain phenomena, and to predict and to quantify. Of course, now what's happened is that in developing the framework for K-12, in writing that document, the idea was that was going to be the basis for the next generation science standards, and that those standards should be written in terms of performance expectations. And so now you have a new architecture for standards, which is stating the standards in terms of these performance expectations that are ostensibly drawing upon three aspects of the NRC framework: the science and engineering practices, the disciplinary core ideas, and the cross-cutting concepts. This, when we start to look at it, is a much more deeply articulated sense of what we want kids to know and be able to do, because it's stated in terms of performance expectations, but it leads to all sorts of issues of assessment challenges. Because in fact, as we know, standard statements, whether they're written in the typical way or as a form of performance expectations, do not immediately lead to assessments. They still have to be interpreted in terms of the assessments. And so one of the things that I want to pose is that now that we have articulated in the framework and the standards what these performance expectations are, that in a science article that was published recently, I was asked to identify what are three grand challenges for science assessment. And the first of them is to really design valid and reliable assessments that reflect the integration of the practices, cross-cutting concepts, and core ideas. And this is not something that we've done before. Typical science assessments have either assessed content knowledge or they have assessed what you might call practices of inquiry, which take various forms that are decoupled from content. And we have never really connected the two or the three in terms of what it means to assess these performance expectations. And as argued in this, that this research has to be carried out in instructional settings where students have had an adequate opportunity to learn, and teachers have had the adequate opportunity to instruct students to develop this kind of integrated knowledge. So one challenge is just essentially thinking about the design of valid and reliable assessments that reflect this, and I'll get more to that in a minute. A second is to actually use assessment results to establish an empirical base regarding progressions of science proficiency in K-12. We know that much of what's assumed in the next generation science standards and in the NRC framework talks about learning progressions. And learning progressions are a great idea, but we also know that much of what is hypothesized is exactly that, a set of hypotheses lacking a strong empirical base that needs to be verified. So one of the things that is that actually assessment can serve as a way in which we can build an empirical knowledge base that will tell us about some of the hypothesized progressions and help advance our knowledge. And the third is that for assessments to be really valuable, they have to be usable in instruction. And so we need to build and test tools and information systems that help teachers effectively use assessments to promote learning in the classroom. And in fact, one could argue that our emphasis initially in terms of assessment related to the next generation science standards should be focused at the classroom level, not at the large scale level, because we have to co-develop this in the context of supporting teachers in developing the instruction and the curricular activities and the assessments that will allow students to develop the proficiencies that we want. But we also know that in order for them to do this and to implement effective assessment practices as part of their pedagogy, they're going to need support. They're going to need tools and technologies and information systems. So let me sort of try to make a case for where do we stand in meeting these challenges? And what's something that we can draw on that will help us understand better how big a challenge this is, but also some ways we can begin to move forward on it. And I would argue that we do actually, in science, have now, with the articulation of the framework and the next generation science standards and some other things, a much better sense of what the development of competence should mean, as well as the possible implications for designing coherent science education. And we also have examples of thinking through, in some detail, this idea of juxtaposing disciplinary practices and core content knowledge to guide the design of assessment. And I'm going to take you through a little bit of the history of the AP redesign project, since that's one that I was intimately involved in, and it's still an ongoing enterprise. And I want to use it to exemplify essentially a way in which we can approach this problem and give a sense of the scope of the problem, but also what's possible when we give it adequate time and thought and invest the resources, and then come back to how do we take what we've learned from AP and think about what the challenge is ahead of us with respect to the rest of K-12. Because AP is admittedly a very selective case. It's at the upper end of high school. It's at the point of transition from high school to college. And yet, it is the precursor of everything that we've seen now in the NRC framework and the next generation science standards. I would also argue, but we don't have time today, that there's a lot of R&D projects that have been supported over the last decade that give us good examples of how to use technology and design to build actually very interesting science assessment tools and materials. And maybe we can talk about that in questions. So for those of you who don't know, the AP Science redesign came about as the product of an NRC report. By the way, an NRC report I had nothing to do with, okay? That was highly critical of advanced study of math and science in the U.S., both the AP program as well as the IB program. And it recommended some fundamental changes that needed to be made in all the AP courses. And it included emphasizing deep understanding rather than comprehensive coverage. One of the things that had happened in AP courses, because of how they were built, they were designed to mimic the first-year course. And so what it meant was you took the first-year syllabus and you took all the topics and you crammed that into the AP course. And you built an exam that covered all those topics, and a lot of it was memorization. And so you had the same issue, the mile-wide, inch-deep syndrome that was true in AP. That's also true in freshman courses at the university level. That you needed to reflect deep current understanding of how students learn in a discipline, current research directions, and emphasize the development of inquiry and reasoning skills. So this was a project that was supported by NSF and the College Board. And the goals were to produce a more inclusive and more engaging program of study, and to do this by identifying what concepts really should students know, and what kind of reasoning and inquiry skills are supposed to be supported in the instruction and measured in the exams, and what kind of practices were going to help, and what kind of resources would teachers need to have to be able to do this, with the goal of creating a program that that engaged diverse student populations, supported teachers, and continued to support what was a major goal of the AP program, which is the awarding of college credit placement for qualifying student exam performance. So you have to understand that the AP program, in sort of thinking about this, was flirting with disaster, because they have a very successful program, and that program's been going for almost 50 years now, and they have a strong clientele, and the issue was, are you going to change this? And what's going to happen with respect to your clientele, and particularly with respect to the higher education community? So in 2006, with support from NSF, we embarked on a big project to redesign the AP Science courses and exams. And basically, in doing this, we built on a variety of conceptual inputs. Understanding by design, how people learn, knowing what students know, and evidence-centered design. And I was the PI on this project, along with Gene Pemberton, who's a chemist at Arizona, University of Arizona, and Mark Ricase, who is a measurement specialist at Michigan State. And there's a large cast of characters. So one of the things I want to emphasize is that you don't do this work without a large interdisciplinary team, because the scope of this is enormous in terms of what you're trying to do. And to give you a sense of how long it takes to do this, if you notice, that timeline starts in 2006. And this is 2013. As I sometimes say, it takes a lot of time. There's a line in an old song that's called, it said, it takes a lot of time to turn the Titanic around. So these are all the components all the way up through 2013. And to give you a sense, we started this work in 2006. This month, the first redesigned AP exam is being given in biology. Next May, chemistry will come online. The May after that, physics will come online. So I think it's important to understand, even with a lot of resources and dedication and the willingness of an entity like the College Board to take on this work, it takes quite a bit of time to actually engineer this, because you're not just engineering an assessment. You're actually engineering an entire curriculum framework as well as an assessment program. And I'll sort of elaborate on that. So I'm going to talk about this in terms of three critical phases that we worked through. The first we call, and this is using a sort of evidence-centered design perspective, what we call the domain analysis, and then developing a domain model, and then an assessment framework. So the domain analysis is really taking the discipline down to its core with disciplinary experts and asking what are really the core ideas in this discipline that we want students to know and understand. And to do this, we assembled disciplinary experts and we gave them a framework that said, okay, chemistry, tell us what are the 4 to 7 big ideas or unifying principles of your discipline. And then, with respect to those, what are the enduring understandings of the discipline that build up to and that are connected to those big ideas? And so each disciplinary group was basically instructed, you've got to come up with 4 to 7 big ideas. And then you can elaborate that in terms of enduring understandings, and then you can go down to the level of specific elaborating details or contexts that help develop that. We also said that there's a part of this framework which is the reasoning and inquiry skills. So each disciplinary group was assembled with the idea, we're going to build this out over time through constructive discussion, argument, etc. That's going to be a collaboration between disciplinary experts and learning scientists. So there's occasions in this where disciplinary experts would develop a set of candidate big ideas or enduring understandings, and if they couldn't agree, it was like Survivor. They would vote them off the island. Not the persons, but the ideas. Okay? So one of the things that we had to be sure of was also, is this representation, which is developed by disciplinary experts who are both at the high school level and at the university level, including major researchers, is it going to pass muster? So there was elaborate peer review. It felt a lot like this. And it went through multiple cycles. And the result was a representation that you can sort of think of at this level graphically, that there are big ideas, there are enduring understandings embedded under those big ideas, and there are supporting understandings embedded under those enduring understandings. And that was elaborated graphically and in narrative text in each discipline, biology, chemistry, and physics. The other part was to deal with what we call the cognitive framework for reasoning and inquiry skills. And this we found out that the disciplinary experts were not very good at doing. When we asked the disciplinary experts to generate this, we got varying lists depending upon what discipline. So this is where we brought in the learning scientists, who also had disciplinary knowledge, who worked with the disciplinary group, and we produced a set of AP science practices that transcended all the disciplines. And this is the first, what I call the first level of representation. So these were the practices that came out of that. Use representations and models to communicate scientific phenomena and solve problems. Use mathematics. Engage in scientific questioning, etc. Perform data analysis. Work with scientific explanations and theories. And one important one that came out was connect and relate knowledge across various scales, concepts, and representations in and across domains. So this is a very high-level statement of the practices, which was then taken to a more elaborate level. So if we take this one, work with scientific explanations and theories, what does that mean? Well, level 2 is, it means justifying claims with evidence. It means constructing explanations of phenomena based on evidence produced through scientific practices. Articulate the reasons that scientific explanations and theories are refined or replaced. Make claims and predictions. And evaluate alternative scientific explanations. So we gave meaning to the first level of practice in terms of a second level, but we gave it a third level as well. For each of those first 2 levels, we essentially said, what is the evidence that a student has that competence? So if we sort of say that we're interested in arguing that a student has the capacity to work with scientific explanations and can justify claims with evidence, what observable data would be needed to support that claim? And so we laid that out as well in terms of this framework. This was done for all of the sciences simultaneously. Then the issue, so what we ended up with was something that might look like this. We have, for each domain, we have a content description, core ideas, disciplinary ideas, and we have a set of science practices. That constituted what we call the domain analysis. Okay? But it doesn't, it's part one. Now we had to move to the domain model. And the domain model is essentially, how are we going to express this in a framework which states a set of claims and evidence that we want to make about the competence that students would have as a result of the course that they take in AP chemistry or biology. And so to do this, we essentially now used evidence-centered design and sort of said, okay, what claims do we want to be able to make about students in AP biology in terms of what they're supposed to know and be able to do, and then what would be the evidence that would constitute support for that claim, including how you would analyze and interpret that evidence before we ever think about designing tasks. And the way that this was done in all of the disciplines was through the intersection of the content and the practices. And I'll show you that in a minute, because that is the basis also for understanding the next generation science standards. So what do I mean by this? Let me illustrate the process of going from the domain analysis to this domain model. So let's take a big idea, an enduring understanding, a supporting understanding, and a science reasoning practice, and see how the domain experts with the learning scientists created a set of claims and evidence statements. So one of the big ideas in chemistry is that chemical and physical properties can be explained by the structure, arrangement of atoms, ions, or molecules, and the forces between them. The enduring understanding is related to the strong electrostatic forces that hold atoms together, called chemical bonds. And then you have the third level, which is covalent bonding. And then sort of here's one of the levels of the so-called reasoning skills. The students can justify claims with evidence. So the claim now gets elaborated in this way. The student is able to use evidence to justify claims involving the classification of covalent bonds in terms of the polarity and the relative strength of the covalent bonds. And when all is said and done, you end up with something that looks like this. That's the claim you want to make about what the student knows and can do, and the evidence that comes from the elaboration of the practices has now been instantiated with respect to this specific content. I haven't yet shown you an assessment task. This is all essentially to lay out a model of the competence and what kinds of evidence we want the students to be able to show at the end in terms of the claims we want to make. It's translating the core ideas and the disciplinary practices into a framework that can support two things: curriculum and instruction and assessment. So one of the ways we like to represent this is that this domain model of claims and supporting evidence, and I won't talk about achievement levels now, gives rise to two things that are coordinated: a curriculum framework and an assessment framework. And so what it did was it drove two things that went on in parallel as the next steps to carry this work in each discipline forward. It led to a curriculum framework which was articulated for biology and chemistry. And that curriculum framework, essentially, here's the structure of the AP Biology curriculum framework. There's four big ideas in biology. There's a set of enduring understandings, essential knowledge, science practices, and these come together to define learning objectives. And if you look in the AP curriculum materials, you will find described the big ideas, the enduring understandings, etc., and you will find the learning objectives. Those learning objectives are essentially performance expectations. They were supposed to guide what it is that teachers are supposed to be helping students be able to do, guide also the design of the assessment. So just to give you an idea of what are the big ideas in biology, one is the process of evolution drives the diversity and unity of life. There are certain segments of the American population who aren't fully enamored with that big idea, but be that as it may. Second big idea, biological systems utilize energy and molecular building blocks to grow, reproduce, and maintain homeostasis. The third is about information, how living systems retrieve, transmit, and respond to information. And that is across all levels. And then biological systems interact, and these interactions possess complex properties. And if you look in the framework, all of these are described in some detail, and then they are essentially laid out. So if we look at evolution, there's 4 enduring understandings. And it has to do with change in the genetic makeup of a population over time. That defines evolution. Organisms are linked by lines of descent from common ancestry. Life continues to evolve within a changing environment. So evolution is not a past event. It is what we are living in right now. And that the origin of living systems is explained by natural processes. So integrating the content of the science practices, as I said, leads to essentially content, science practice, and a learning objective. In this case, essentially, the student is able to evaluate evidence provided by a data set in conjunction with a phylogenetic tree or a simple cladogram to determine evolutionary history and speciation. Okay. So you begin to get a sense of what it is that the student is supposed to be able to do to demonstrate that they know and understand this. It is expressed in terms of a practice or a set of practices related to some core ideas and principles. Teachers are given choice. One of the problems that teachers have always had is, oh, I've got to cover every example case. So if you're thinking about genetics and genetic disorders, because we never know what's going to be on the exam, etc., so teachers would start to say, oh, I got to cover sickle cell, I got to cover Huntington's, I got to cover Tay-Sachs. And so what happens is the students get exposed to a bunch of examples, but they never get the principle. This idea is essentially to convey this important idea. Essentially, you choose an illustrative example and you develop it in depth. And that's the point. We're not going to test students about their specific knowledge about Huntington's or about Tay-Sachs. We're going to test them about their understanding about these genetic disorders and how they play out in important chromosomal issues in genes and traits. The course also leads to significant changes in labs. So a whole new set of AP labs were designed, and you can sort of see a set of issues here in terms of okay, what are the key factors, and what was done previously in AP labs, which has a great deal of similarity, by the way, to most college-level labs, and what the new labs look like in terms of how they're structured and designed. So instead of the question being framed in the lab, students generate their own questions for investigations. Instead of the alignment being unclear between the lab and the curriculum, essentially the labs are now tied to big ideas. They are tied to specific aspects of that curriculum framework. Rather than the experiments being teacher-directed, students design and conduct their own experiments. Rather than students being told what variables to investigate, the students choose which variables. In fact, they have to argue what variables are relevant. This is all, and if you think about this in terms of those practices, this is a way in which you develop those practices through the laboratory activities wrapped around content. So what the domain model gives rise to is a much changed curriculum framework. And that curriculum framework is structured the way I've said. That's true for biology, it's true for chemistry, it's true for physics. So these set of design principles and this sort of model is being replicated across each of the AP science disciplines. Now I'm going to turn a little bit to the assessment framework, just to give you an illustration of how the AP exam has changed. So the third part of this is to go from the claims and evidence statements, the domain model, to an assessment framework. And in evidence-centered design, that means developing task models and building what amounts to a large-scale assessment, which is no small task. So in the new AP exam, there's no test items that will focus on low-level cognitive skills. There is no item that just is pure declarative knowledge recall. In fact, for each item, students will either produce the evidence in a constructed response, or they'll engage with the evidence in a selected response or multiple choice item. And I'll give you some illustrations of that. And I have to admit, this is still very much a work in progress, even though the first AP biology exam is being administered this month. So what's different? Well, the first section of the AP biology exam essentially now consists of 63 multiple choice and 6 grid-in questions. I'll show you what that is. A considerable reduction relative to what AP biology was before. In addition to the change in the kinds of multiple choice items, it's different in terms of the mixture. The section 2 involves response questions, free response questions, 6 of which are free response, short free response, and then there's 2 long free response questions, one of which is lab-based. That is, it is related to the set of laboratory activities that were supposed to have been engaged in the course over the course of the year. And you see that the weighting is now 50-50 on this. So one of the things I have to say about the AP program is we would have liked them to go further in the assessment design and not put it all in the large-scale test, which is still paper and pencil, by the way. But you can only turn the Titanic so far. It's a slow process, okay? And I think they're actually understanding other changes that they need to make. Here's a kind of sample multiple choice question. It just gives a context of 2 flasks. They have identical media, etc. And the question now is essentially, from these choices, which of the following best predicts which culture will contain more yeast cells and most accurately justifies that prediction? So it is essentially trying to move to multiple choice questions that get more at the practices related to the content, even in a selected response item. And I should say that in the process of developing these items, cognitive labs were done, a lot of field testing was done to make sure that these items actually got at the kinds of reasoning. There was a new question type developed, which involves student-produced responses, grid-ins, in which rather than picking numbers, and essentially students now actually have to apply the math and then use the response by gridding in the number so that it can still be machine scored, but this allows them to no longer just guess what's the right number and actually apply the mathematics. So here's an example. The data below demonstrate the frequency of tasters and non-tasters in an isolated population at Hardy-Weinberg equilibrium. I don't know what Hardy-Weinberg equilibrium is. I have a little bit of an idea, but they're supposed to know what that is. The allele for non-tasters is recessive. How many of the tasters in the population are heterozygous for testing? And then, given what's there, figure that out and grid in the response. And here's an example of a short free response question. Again, there's a context established. The role of tRNA in the process of translation was investigated by the addition of tRNA with attached radioactive leucine to an in vitro translation system that included mRNA and ribosomes. The results are shown in the graph. In a short paragraph, describe how the graph justifies the claim that the role of tRNA is to carry amino acids that are then transferred from the tRNA to growing polypeptide chains. So they have to now construct an argument using the evidence and their knowledge about this area of essentially RNA and proteins. And again, for each of these items, there's an elaborate evidence scheme in terms of what you are looking for in the constructed response, because that was part of trying to design the situation, because the situation comes from a task model that's driven by the evidence model. What's the impact? One impact is because of the use of big ideas in structuring the exam. In 2008, 12% of the questions had something to do with evolution. In the new exam, 35% of the questions have something to do with evolution. It's a big idea. Okay? It ought to be very highly represented in what the makeup of the exam is. Because of the emphasis on science practice and math skills, new types of questions are being asked. And because of the use of evidence in the design of the assessment, the number of multiple choice questions was reduced from 100 questions to 63. And one of the reasons why there were so many multiple choice questions was largely because they wanted to stabilize the scores, and they wanted to do the linking. It was driven by the psychometrics, not by the substantive needs. Now, when you've got an evidence-driven process of design, you can reduce the number of multiple choice questions, which tends to give you higher reliability for purposes of linking and estimating, and essentially shift what those questions are doing in terms of the makeup of the exam. Immediate impacts of the AP biology changes. This curriculum framework was put out, so this is 2013. This curriculum framework was published in the prior to the fall of 2011, so that teachers would know 2 years in advance what the new AP biology was about, and they could start working on changes in their instruction over a 2-year period. The curriculum became active in this academic year, and the exam in biology is this spring. Chemistry follows a similar pattern. The framework was put out in 2012 for an exam in 2014, and physics will come out now for an exam in 2015. So there was lead time and support for teachers. Many teachers had to replace all their labs, and they had to incorporate inquiry throughout the course. And many of them struggled to incorporate mathematical skills. So this is still an ongoing process, and 180,000 students are taking the new AP biology exam this month, for which standard setting will be done this summer. So it gives you some sense of remember, we started this in 2006, and we worked it through all these steps, and it's 2013 now, May, when this first actually the high-stakes exam hits the streets and the students are subjected to responding to this kind of an exam. We don't know what the performance is going to be. It's going to be very interesting, and I would expect that performance on this AP exam will get better over time because people will have a better sense of the exam, but they will also have changed the instructional practices and the curriculum. So what did we learn from the AP redesign? No pain, no gain. This was very hard work to do, even within the constraints of an organization that has complete control over the curriculum and the exam. Okay? Remember, this is the College Board, and they own this. It turns out that using the complementary methods of backwards design and evidence-centered design are really challenging to fully execute and sustain. Only way to do this? Multidisciplinary teams. The disciplinary experts couldn't do it. The learning scientists alone couldn't do it. The psychometricians alone couldn't do it. It required essentially those groups working together continuously in interaction over time, negotiation, and needless to say, it requires time and money and a whole lot of patience. And sometimes that's a precious commodity in certain organizations. What's the value added? If we think about this from the point of view of validity, validity in some ways is designed in from the start as opposed to grafted on after the fact. at least aspects of a validity argument are contained in the process and the products in terms of explaining what you did and how it's represented. Now, there's a lot more validity work that continues to need to be done, including whether students who score 3 or higher on this exam are going to do well in college courses. That's another form of validity that one would want to see. So it's all part of constructing a validity argument. So let me bring this back now to K-12 and try to sum up some things in terms of how do we learn from the AP example and think about now the challenge of not just transforming AP, but transforming K-12 science education as represented in the framework and the next generation science standards, because this is the architecture of the standards. And we've never seen standards like this. And on the other hand, these standards, unlike the Common Core standards in English language arts and mathematics, were the products of multiple inputs, multiple states participating, a lot of argument, but they hold true to what the NRC framework laid out there. But they pose major assessment challenges and major instructional challenges. So those standards now are the basis for aligning curriculum, instruction, and assessment. And we know just yesterday, or not yesterday, about a week or so ago, less than a week, there was an article in Ed Week about the challenges of the next generation science standards. How much it's going to take to move in that direction, both in terms of curriculum and instruction and assessment. So what are some of the challenges for assessment? Well, we've got to develop assessment tasks that integrate the 3 dimensions. We've just never really done that, okay? Except somewhat in the context of AP. We've got to develop tasks that assess where a student can be placed along a sequence of progressively more complex understandings. Because now it's not just at the upper level AP, it's along learning progressions. And we need to develop assessment tasks that measure the connections between the different strands of disciplinary core ideas. So think about this one. When I talk about biology, we're just talking about biology. I talk about chemistry, I'm just talking about chemistry. In the next generation science standards, you've got life science standards, you've got core ideas in life science, in physical science, in earth and space science, and in technology and engineering. So those need to be also coordinated with each other because there are important interactions among those. Quickly, 5 things to consider for us while moving forward that all have implications. The first one, assessment context, purposes, and uses. Educational assessment, probably don't need to remind you folks, typically occurs in multiple contexts. It occurs in small scale in individual classrooms, intermediate scale, and large scale. And within and across these contexts, it can be used for multiple purposes. Assist learning, measure individual achievement, evaluate programs. So we have a multiplicity of actors and needs. And the reason we have so many different forms and type of assessment is a good one. One size does not fit all. So we have to remember what we're designing is for educators at different levels of the system that need different information on different time scales to make it usable. They have differing priorities, they operate under different constraints, and they operate in terms of the type and level of information that's needed. So that's one of the design issues facing us. We've got to design for multiple context, uses, and purposes. Second is the nature of assessment and the importance of research on learning. As argued in Knowing What Students Know, assessment is fundamentally a process of reasoning from evidence. It hinges on 3 things: our models and theories about what it means to know and how to develop competence, the observations, the tasks, situations that we ask students to respond to, and the way we make sense of the data. And a really good assessment depends on these things being coordinated. And models of development of domain knowledge are critical to this process because they tell us what are the important aspects of knowledge we should be assessing, give us clues as to how that might be assessed, and they can lead to assessments that yield more instructionally useful information, as well as they can guide the development of systems of assessments that are intended to cohere across grades, across contexts of use. I'll come back to that in a minute. So we have information about learning progressions in science. We're developing that. It's of varying degrees of agreement. And we face the Goldilocks problem in learning progressions. And what do I mean by the Goldilocks problems? We haven't solved this with respect to learning progressions. Not too big, not too little, just right. Essentially, what's a useful learning progression to use in science to guide this work? Not too many things, not too few things, just the right grain size. And as Margaret knows in various contexts, there are debates and arguments as to what's a learning progression and what's not, and what are how best to use this. On the other hand, this is a really important idea to think about in this whole game of assessment. Assessment design. Anybody who's worked in assessment design knows that assessment design spaces vary tremendously and they involve multiple dimensions. And some of the factors related to that are type of knowledge and skill, time period, use, availability of detailed data and theories, and even the distance from instruction and assessment purpose. That there are things that are close to instruction, there are proximal and distal, and all of this is part of a very multivariate design space. So we need principled ways to do this that can help structure going from theory, data, standards to operational assessments. And I would offer that evidence-centered design gives us a set of ways to think about this in terms of what I call a very productive engineering approach that uses theory to guide what we're doing. Affordances of technology. AP doesn't use technology. I think it's a weakness. And I think this is a claim that we have to embrace and recognize in science, that much of what's new, different, and important in the NRC framework and the next generation science standards cannot be adequately assessed by conventional methods, items, and measurement models. The capacity to engage in the practices really requires that students be able to show things that aren't just tested in paper and pencil format. And we're interested in the processes of thinking as well as the products. So one of the things is technology opens up all sorts of opportunities. And if we had more time, we could talk about some of the demonstration products that have shown us what we are able to do with technology to get at forms of reasoning and argumentation and use of evidence and modeling. Because technology can do all these things, it can do it in science. It could also do some of this in English language arts and mathematics as well. And in fact, very little of what we're talking about the affordance of technology is actually being used in PARC and Smarter Balance. But that's another conversation. Last one, systems of assessment. We don't just want one thing. We want a multi-level system. We need a multi-level system that fulfills functions that are needed at each level. It has a clear set of intended users of the information. And the tools need to be designed to serve the purpose. And the levels have to be articulated and conceptually coherent. They can't be at odds with each other in terms of trying to measure things that aren't from the same conceptual base. So it doesn't matter what your grain size is. They should be consistent, even if you've got a very rough grain size versus a very detailed grain size. And so the key design elements in building this is the system is designed to track progress over time, and it uses tasks, tools, and technologies appropriate to the desired inferences. Okay? Easy to say, not so easy to do, because it describes what we have still to build. What's left to, this is probably the understatement of the year. Okay? There's a lot that we have left to do, but we have a framework and a basis to work. We need to translate the standards into effective models and methods and materials, not just for assessment, but for curriculum instruction and assessment. And we need to evaluate and use what we know already to evaluate and improve the assessments that we have right now, as well as developing new ones. It's not like we have to throw out all the assessments we have right now, but we need to look at them in terms of what aspects of science competence they're really adequate or even how to improve them. We're doing some work on concept inventories in higher ed in terms of trying to look at them from this very same perspective in terms of what can they do relative to the kind of knowledge we want. But there's a lot of work to do there. One question is whether or not we have the will such that we'll have assessments that are worth teaching with and to. And I worry about this. The policy community can jump in and say, oh, we've got the new standards, build a new large-scale state test. Okay? And hopefully, essentially, for science, we can hold them off a little bit on that. We can hold them off from essentially leaping to building the PARC and smarter balanced version for science that we have now started to build for ELA and mathematics. Because in the end, as just was true for ELA and math, standards are the beginning. They're not the end. They're not a substitute for the thinking and research that's needed to define the progressions of learning that can serve as the basis for the integration of curriculum, instruction, and assessment. So we have to avoid this, that assessment cannot be the tail wagging the educational dog. That we've got to think in terms of an integrated system of curriculum, instruction, and assessment that flows from a deep sense of the standards and the theories of learning and knowing. And of course, in doing this, we also have to recognize we're not going to be perfect, and we have to remember Voltaire, and that we have to avoid the idea that we have to remember that the perfect is the enemy of the good. So in doing this, the standards aren't perfect. A lot of what we're going to do is not perfect. But it gives us a way to move forward. Thank you.